Hi students, good morning, welcome back to our physics classes. So during the last class we have seen we have stopped with some terms related to radiation, and these are absorptance, reflectance, transmittance, spectral emissive power, then absorptive power and spectral absorptive power, and finally emissivity. Then we have defined a black body. So what is the property of a perfect black body? A body, we can say that a surface or a substance or a system which can absorb all the radiations falling on it. Nothing is reflected, nothing is transmitted. Such a system is called black body. And why it is called black body? Because nothing can be escaped from that surface. That is why it is called black body. That means generally we are saying that an object absorbs everything, it is appear in black in color. But it is not necessary that a black body should be black in color. It is not necessary that black body should be black in color. But any substance, any surface, any system which can absorb all the radiations falling on it can be considered as a black body. Okay, so that is the concept of a black body. And today we are going to define two laws regarding black body radiation. And how we are saying that if a system is good absorber, at the same time it should be a good reflector also. Not reflector, it is an emitter also. It can't reflect, but it can emit its own radiations. Okay, so a good emitter is a good absorber. A good absorber is a good emitter. So, black body radiator or black body radiations. We are studying more about the black bodies with the help of the radiations coming out from the black bodies. So, these are called black body radiations. So, related to black body radiations, two laws we have to define there. Two laws we have to define. One is Stefan's law. First one is Stefan's law. So Stefan's law says about the emissive power and temperature of a relation between emissive power and temperature of a black body. It says that emissive power of a perfect black body is directly proportional to fourth power of its absolute temperature. Emissive power of a perfect black body is directly proportional to fourth power of its absolute temperature. That means E proportional to T to the power 4, where E is the emissive power and T is its absolute temperature. And it is given that E is equal to sigma T to the power 4, where sigma is known as the Stefan's constant. It is known as the Stefan's constant. Okay, so E is equal to sigma T to the power 4 is Stefan's law. That means emissive power of a perfect black body is directly proportional to fourth power of its absolute temperature. Okay, that is what is emissive power? Radiant energy emitting per unit area per unit time. That is Q by T. So we can have Q by T or E is equal to sigma T to the power 4, where sigma is the sigma is the Stefan's constant, and its value is 5.67 into 10 to the power minus 8 joule per second per meter square per Kelvin to the power 4. Joule per second per meter square per Kelvin to the power 4. That is 5.67 into 10 to the power minus 8. Sigma, value of sigma is 5.67 into 10 to the power minus 8 joule per second per meter square per k to the power 4. Okay, so that is Stefan's constant. Stefan's constant is 5.67 into 10 to the power minus. It's easy to remember. 567 10 to the power 8 with a negative sign. Okay, so E we have already said that is Q by T emitting radiant energy emitting per second per unit area. So that is the Q by T, that is E is equal to sigma T to the power 4, that is Stefan's law. And suppose you are having a black body, and that black body, and I already told you black body is not a alien thing. We can't say that it is an alien thing. You can make your own black body. If you are having a lead shot, and you are making a cavity in that lead shot, in such a way, if the radiations are falling on it, it is totally internal reflections are happening from all the surfaces. That means it can't reflect it back, or the radiations are not coming back from that lead shot. So that lead shot can be considered as a black body because all the radiations falling on it is getting absorbed and nothing is reflected, nothing is transmitted. So this is a black body. Suppose it is kept in a, and its temperature is T, and it is kept in a cavity, and the cavity surrounding temperature is T0. And you know, it is emitting, the emissive power of that is E proportional to T to the power 4. But at the same time, it is a good absorber also. From these, T0 to the power 4 amount of energy can be absorbed by that. So the net emissive power will be E equal to sigma into T to the power 4 minus T0 power 4. E is equal to sigma T to the power 4 minus T0 power 4, where T is the absolute temperature of the black body and T0 is the surrounding temperature. That means the cavity temperature. Okay, so that is Stefan's law, that is emissive power of a black body is directly proportional to fourth power of its absolute temperature. So that is the first law related to the black body radiation. Now we can go for the second law, and the second law talks about the radiant energy coming out from a black body, changes in the radiant energy coming out from the black body with respect to its temperature. And we have already seen that from this Stefan's law, when the temperature rises, the emissive power also rises. And when you are having, suppose a black body is there, and that black body is kept at different, suppose similar black bodies are there, and they are kept at the, if you are having one black body, it is kept at a temperature T1. So it can radiate a stream of energy. That means its radiant energy, we can it can emit any radiations. That means a good absorber is a good radiator also. So it can radiate any kind of radiations. So when you are considering it can emit any kind of radiation depending upon its nature and temperature. That is important. Okay. And suppose you are having spectrum, that means different wavelength are emitting, and corresponding energy also you are plotting between x-axis and y-axis. So lambda is taken along x-axis and energy is taken along y-axis. Okay, so all the radiations are not having the same emissive power. That means all the radiations are not emitting at the same intensity, we can say like that. Which means the radiant energy is different for different wavelength. Radiant energy is different for different wavelength. So for a particular particular temperature T1, you are getting a graph like this. That means for a particular value of lambda, that is the case when temperature T1, this is lambda 1, you are getting maximum energy emission. Different radiations are emitting, but maximum radiations are coming out this particular wavelength, lambda 1, at the particular temperature T1. Suppose you are increasing its temperature to T2. Then you are getting another curve. Like this. What it indicates? Here, maximum energy radiant energy wavelength is lambda 2. This curve is for temperature T1 and this is for T2, a higher temperature. And again you are increasing the temperature to T3 and then you are getting a curve like this, which means this lambda 3. And the total area means for a particular curve, the area enclosed by that is the emissive spectrum, total emissive energy, but it is maximum for a particular wavelength only. That means maximum energy emitted radiation occurs only at a particular temperature, lambda 1, lambda 2 and lambda 3, at different temperatures T1, T2, T3. We are interested in lambda 1, lambda 2, lambda 3 with respect to T1, T2, T3. As the temperature increases, lambda goes on decreasing. Lambda goes on decreasing. What is the property of lambda 1, lambda 2 and lambda 3? These are the wavelength of maximum energy emitting radiation. That is the wavelength of maximum energy emitting radiation. So we can say that as the temperature of a black body increases, maximum energy emitting radiations move towards shorter wavelength. That means wavelength goes on decreasing as the temperature increases. Maximum energy radiations are having shorter wavelength as the temperature increases. T1, T2, T3 as the temperature increases, then lambda 1, lambda 2, this goes on decreasing. That means maximum energy emitting radiation displays towards shorter wavelength as the temperature, absolute temperature of black body increases. And this is known as Wien's displacement law. This is known as the Wien's displacement law. What is displacing here? The maximum energy emitting radiation's wavelength is decreasing as the absolute temperature of the black body increases. So as the maximum, as the absolute temperature, as the temperature of the black body increases, the maximum energy emitted radiation displaces towards shorter wavelength. That is Wien's displacement law. That is Wien's displacement law. Means Wien's displacement law, WIENS. Wien's displacement law. Okay, and when we can have lambda m is the maximum energy emitting radiation and T is the absolute temperature, then there is a relation between lambda m and T, and you have to learn that expression, that is lambda m multiplied by T. Lambda m into T is equal to B, where B is a constant. That is T and lambda m are inversely proportional. That we have already seen. T and lambda m are inversely proportional, so T into lambda m should be a constant, and that constant is that constant value. The constant is B, and its value is 2.9 into 10 to the power minus 3 mK meter Kelvin. So 2.9 into 10 to the power minus 3. So B is equal to 2.9 into 10 to the power minus 3 meter Kelvin. That is Wien's displacement law. Wien's displacement law says that as the temperature of a black body rises, maximum energy emitting radiation shift towards the shorter wavelength. So that is two laws, Stefan's law and Wien's displacement law. Okay, so we have seen three kinds of heat transfer: conduction, convection and radiation. So now one more topic is left in this chapter, a short topic is left in this chapter, that is Newton's law of cooling. With that, we will finish up with the chapter heat transfer, and that is the last topic for your second semestral exam. So for your second semester, the portion is arranged like this. We are starting with the moment of inertia that we have started with the second semester, and up to the last content heat transfer. Okay, all those chapters are you can expect the questions from these chapters for your second semester examination. Okay, so start prepare. Means this month you are having the by 23rd you are starting with your examinations, and prepare well. Start revising the chapters, and from the next by the next class we will wind up with the portions for the second semester examination. Okay, so that's all for today, and you can watch some other animated videos also I am uploading now, so that you can watch. Okay, we'll meet in the next class.